This is question number 2, medium level, and the question has to do with, again, method of substitution. So this question has to do with evaluating the definite integral. So by definite means the interval is specified. So here, and the interval is usually not that big. It's quite a reasonable small range. So here it's going from e, natural number, to e to the power of 2. And you can sort of make sense of the function that is given because you've got cosine. It looks somewhat complex, but there is this ln function here. So by the time you substitute these values, it will sort of cancel out. It's not going to be left as e anymore. It's going to be left as power of 1 and power of 2 and so forth. So you will see that as we solve the question all the way through. So here again, when it comes to method of substitution, it is directly linked to chain rule. So you always want to think of chain rule. It's like chain rule reverse. So you're starting from taking derivative, you have a complex function, and you will be going from like f g at x, and taking derivative would be f g at x times g derivative x. But when it comes to integral, it's like reversed operation. So you're going from here, you're starting from here, and you're going backwards and trying to find this expression. And finding the area, this expression will be some kind of a curve over x and y axis on the two-dimensional surface, and this interval is defined over the value of x, and so it's going to be shaded area, and you're basically finding the area under this complex curve. So method of substitution is a helpful tool for us to do that. So here we want to spot this form again, this chain rule taking place, already the derivative form, and so it looks like cosine, something which is in here, and when we take the derivative of this, ln x, obviously it's going to equal to 1 over x, and this denominator, we can split this as a multiplication of two functions, the one in the numerator and the one in the denominator. And so it would make most sense for us. So before you proceed to solve these questions regarding substitution, try to just investigate for a little while and see this chain rule taking place, and so it makes most sense. Usually it doesn't take that long to figure out. It's usually the ones that are in the bracket of some kind of a function like square root or cosine or whatever. So here, let u be pi over 4 ln x. When we take derivative of this, pi over 4 is just a number, and ln x will take the form of 1 over x, and taking derivative with respect to x. So that will equal to pi over 4x dx. But notice when we rewrite this function, it's going to be e to the power of 2 cos pi over 4 ln x, pi over 4 ln x, times 1 over 2x dx. So this is not quite in that form. We cannot make direct substitution as du. So we want to see what it looks like, what that looks like. So cross multiplying, we can multiply both sides by 2. So when we multiply both sides by 2, we're going to have 2 du, which is equal to pi over 2x dx. This looks more like this form right here. We just have to get rid of this pi, then we're finished. So then it's going to be 2 over pi du, which will equal to pi over 2. Oh, sorry, we've got rid of pi. So it's going to equal to 1 over 2x dx, which matches exactly this form. So what we have to substitute is that once we have made this whole thing to be u, this thing will equal to what we found here. That is equal to this, so we will be plugging in this into here. Another very, very important thing to do when we're using substitution is never forget to convert these into some kind of g at b, and this will be g at a. Normally, integral goes from a to b, and these e and e to the power of 2 can be considered as a and b. But when we are doing substitution, then these are x's, but now we are letting u be g at x. So if x goes from a to b, then u will go from, because these were x's, g at a to g at b. So we need to make that substitution. So to do that, it's very simple. So we are saying, what will u be when x takes on these values? So coming from here, to find those values, we say when x is equal to e, u will equal to pi over 4 ln e. Ln e is just raised to the power of 1. Ln means log base e. Ln and log, they're only interested in with the matching base power. So it's going to equal to pi over 4. And when x is equal to e to the power of 2, then u will be pi over 4. And ln e, so wherever x is, we're plugging in this value. It's going to be e to the power of 2. Ln is only interested in the power, so it's going to be with the same base, and this is log base e, natural number. So we have this times 2. Simplified, this will be pi over 2. So our new converted interval is going to be g at a is now equal to pi over 4. G at b is now equal to pi over 2. So our integral will change according to that. So now we're ready to plug in all this information to solve our integral using substitution. So this will now be pi over 4. And this will now be pi over 2. And now we haven't done anything in terms of cosine. So we say cosine u. And this thing was equal to 2 over pi times du. So now this can come outside of the integral because it doesn't have anything to do with it. So we've got 2 over pi, and cosine is antiderivative of sine. No, derivative of sine, sorry. So the antiderivative will be sine. So it's sine u, and it's going from pi over 2 to pi over 4. In this case, we do not have to substitute back in the original function because according to the second rule of part 2 of the fundamental theorem of calculus, what we have is that when we plug in, so say here we've got now g at a and g at b, and we've substituted with du. We've substituted with f u, and let f at x be the derivative of f at x. And so we have let u be equal to g at x. And so du was changed to, du was equal to g prime x. And so when we just proceed with this without substituting back in, we will have f at x, and this will go from, f at u, and this will go from g b g a. So when we substitute in these two values according to the second part of fundamental theorem of calculus, we've got f g b minus f g a. So that is the answer. You don't have to substitute back in the original variable x. And so here we're left with this. So we're just proceeding with substituting these values. We've got 2 over pi, and we have sine pi over 2 minus sine pi over 4. And these are special angles. And so what's going to happen is that means it's 90 degrees. In 90 degrees, you can think of unit circle. So we've got here x and y. When we have a right angle triangle, we've got theta here. This is opposite, this is adjacent, this is hypotenuse. So this is opposite over hypotenuse. But when you have it in terms of circle, this can be likened to also vertically stretching, so y value, and that is the radius. And that links to Pythagorean theorem, which links to this right angle triangle, and which also links to this circle that's shown on the x and y axis in the two-dimensional plane. So in this case, we've got 90 degrees, and 90 degrees will be shown as this, because we always go from here counterclockwise direction, so that's 90 degrees. And if it's a unit circle, radius is going to equal to 1, and y we have stretched upwards in the positive direction, so it's 1, so this value is 1. So we've got 1 minus sine 45 means this is 45 degrees, and so when we look at 45 degrees, we've got one that's taking place right here, and that's 45 degrees starting from here. And when we draw this right angle triangle, we've got special triangle, which is 1, 1, root 2. So our sine value will be opposite of our hypotenuse, which is y over r, and y is 1, positive, r is square root 2. The radius hypotenuse for this circle is always positive, and so this will be 1 over root 2. So now we've got minus 1 over root 2. So simplifying that gives 2 over pi, and this is root 2 root 2 minus 1. So root 2 and this can cancel out and we've got root 2 left. This will be 2, and when you use distributive property and multiply those two, we will get 2 minus root 2 over pi. And that is our very final answer. And so to answer the question, using the method of substitution, evaluate the definite integral going from this interval right here, this complex function. By using substitution, letting u be some function that is within this bracket, usually it's the complex one, and see the simpler one and see if that's some form of a derivative of the complex function that's within another function. It's usually like square root trigonometric functions and whatnot. And so once you take the derivative, sometimes it's not obvious. You cannot directly substitute du, so you have to rearrange. And once we have rearranged to fit into this component right here, then we just had to put the rearranged form of du. And once we've done that, the constant can come out of the integral, and the rest is just simple. You don't have to you don't have to plug in the original variable back in, because according to this rule, as you have seen the proof here, it works just as though you have taken the indefinite integral and then substituting back in the original variable and then plugging in a and b. It has the same effect. This is a second method, which is a preferred method. It's a lot simpler. So we keep the variable u, and then but instead we have modified these intervals. And after that, remember the special angles, special triangles, and then just calculating and simplifying, and that gives our answer.